Okay, today we're going to be talking about rational functions, and at least being able to factor and find roots and asymptotes of these functions. I'm quickly going to go over a quick overview of how to factor quadratics, and then I'm just going to give you 3 example problems that show factoring quadratics and stuff and other types of polynomials on top and bottom, and then finding roots and asymptotes of these functions. So first of all, what we're going to start out with is going to be 2x squared plus, this is going to be the factoring view, 3x plus 1. Okay, so the way that I would factor these numbers out, well, one way that you can use to factor numbers out that isn't the guess and check one, which is most commonly used because this number is here, is so this other method is like used sort of when you're factoring out when this isn't that way. But one thing to notice, if you haven't been taught this before, is you know how the b, so quadratic function is like ax squared plus bx plus c. So the b number, which in this case is 3, will go in the top, and then the bottom is going to be a times c. Now this little thing here, you're going to fill in these 2 spots with 2 numbers that will add to be letter b and multiply it to be a times c. So with this one, b is number 3, a times c, which is 2 times 1, is 2, and then after that, so what would multiply to equal 2? Well, we could say 2 and 1, which it does, and it does 2 plus 1 equal 3, and it does, so that does work there. So after we do that, you're going to basically move these over to this, you've probably seen this before, maybe, where you can multiply out the little parts of of a factored form, where you could put like x plus 1 and stuff, and all these numbers up here, and then you can just get the whole thing and simplify it into this form. In this, you put the first term, which is 2x squared, and in the bottom right corner, you're going to put 1. Now this 2, you're going to put in either of these 2 boxes 2x, 1x, which would just be x, so I'm just going to put x in the other one. Now, what next thing we need to do is figure out what we can factor out of this row. And what I see that's in common is 2x. In this one, you don't see any variables that are common. There's no x in the one, and there's no other stuff and powers in these. So the only thing you factor out is a 1. In this one, you can factor out an x. Then over here, 2 and 1 don't work very well, and nor does the x, so we can only factor out a 1. And you can also double check this. 1 times 2x is 2x, 1 times 1 is 1, 1 times x is x, 2x times x equals 2x squared. So the factored form of this is 2x plus 1 times x plus 1. This therefore shows that the roots of this polynomial, which would be this number, well, it would be this number over this number. So let me quickly go over that. So that would be 2x plus 1 equals 0. So this would be to figure that out. So you're going to subtract 1, which gives you 1 over here. So that's going to be 2x equals negative 1. Divide that by 2. Divide that by 2. X equals negative 1 over 2. And the way this works is doing the second term over here that you're adding or subtracting, and well, the negative of it, because it would be y equals mx minus b, and that b is, so the root of this function would be b over m. You also have to take into note that there is that minus there that you take out of it, and that's why that turned into a negative 1/2. So the roots of this function would be negative 1 over 2, as calculated from there, and this would just be, since it's simply just a 1 over there, this would be a negative 1, I believe. Yeah, that's what that one would be. Now what we're going to do next is we're going to go over some of the rational functions that I have prepared for this. That's going to be a letter F, functions. Okay, so the next problem that I'm going to have us work on, so the first step to solving these rational functions, this is going to be x minus 1, and rational functions have a format of having a polynomial on the top and a polynomial on the bottom, basically. And it can be anything from the simplest polynomials to really complex multiple power polynomials like cubic functions and all that, and like Dvorak functions, etc. And this one, we're going to basically reuse that same one we did from last problem. So you can try and factor it if you want to, just to see that my method does work, though there will be other times to do that. So that'll probably be on the last problem. So what we're going to do, since this is already factored on the top, we can already assume, so with rational functions, there can be like asymptotes, like if you were to have the function of 1 over x, this would be graphed sort of like this, and going on infinitely in each direction. And this is basically the line that it follows. It never touches 0, this one. And that's because there is no, well, that's because over here, x plus or minus 0, I'll just say minus 0. Invert that, that's just 0. That's showing that that never touches 0. If there's a simplified like part here, when you factor out the parts of these into like different parts of it, if whatever's down here will be the asymptotes where it does not touch. Now up here, if this were to be x plus 1, it would be touching negative 1 also. So it would be like shifted up, I believe, possibly, to have that happen, because it would still not be touching 0. So after that, so this one, the top's already factored, so we can say the roots of this function, the tops will always be the roots. Right here. Roots. This right here will be the asymptotes. Okay. There we go. Which I am actually just going to abbreviate ASSYM with a period. And that's how I'm going to abbreviate it from here on out. So the roots of this function would be the negative of this. So the roots would be 1. It touches 1. So if it were to be one of the graphs, it would probably be coming down and it would touch 1 at that one point where x equals 1. So next thing we need to do is figure out the asymptotes. Now, because this is the same problem we did before, we can basically use the same things that we used to factor it out. If you want to, you can factor it out. I'm going to give you a few seconds. Next, so, oops, sorry for that line. As we had figured this one out, this was 2x plus 1 and x plus 1. And that has the top of x minus 1. And these, there's no terms that cancel out because it's a fraction. So terms can cancel out. I think there's an example of that in the next one, yeah. So the asymptotes will be the same numbers that we used last time because we have the same polynomial that we factored on the last one. So this would be negative 1/2 and negative 1. That's what the asymptotes would be. And that is that problem. Wow, okay. So, the next problem we are going to work on, which I think I'm going to encourage you to possibly try and do, or at least maybe do the first step. This one is going to start out as 2x squared. This is going to, the top's going to be the same as our last one, plus 3x plus 1, all over 2x, I believe. Yeah. Yeah, okay. 2x cubed plus 3x squared. Yeah, 3x squared plus x. Now, you may be thinking that this cubic function is going to be very hard to factor out. But the thing is, the way this one's structured, the one thing that's common among all the terms, as you may have noticed with this one, is x. So, with this one, I'm not going to factor the top one yet because that's the exact same one we used last time. So what you can factor out of this one is x times 2x squared plus 3x plus 1. That just stays there, it's 1x. So you take out the x and you are left with a 1. Now, you notice how it's an x squared problem, so this will be easier to factor using the same method we used before. Now, the b is going to be 3 this time, instead of well, actually, I just remembered. This right here, you can try and factor it out. I'll give you a little bit. So, 3 and 2. This gives you 2 and a 1. And then you can continue on from that point. I'll give you a little bit, a few seconds. You could probably pause the video. Okay, so this part right here and this top part right here, you may notice that they're the exact same. So, one thing we could simply do is technically cross these out. But what I'm going to do is rewrite the whole thing factored. So that's going to be 2x plus 1, then times x plus 1, all over x times 2x plus 1 times x plus 1. Now, because it's a fraction, like terms cancel out. So these ones cancel out, and these ones cancel out. Now, this won't be a 0 because it's always 1 times whatever. So, what we get left with is the function 1 over x, which, in the last question, I had shown you the basic graph of how that was. And this one, I also sort of explained how this is also x plus 0, or x minus 0, because there's no positive or negative 0. And because there is no x up here, there is no roots. So, roots, there are none. Asymptotes, there is going to be one asymptote, and that's going to be at 0 or negative 0, which are the same things, 0. And that's how this one works. Now I'm gonna give us our last and final problem. This one is going to be, I believe, yeah. This is going to be 3x cubed plus 4x squared plus x, all over 2x squared plus 3x plus 1. Now, you may have already noticed that the bottom is the same, that one that I've been using since the beginning. I just did this for simplicity and so that I could create these problems a little faster. So, I'm not going to factor that out. You can factor it out yourself if you would like to, but that's your choice. The top part is what I'm going to be working on right now. Now, you notice that it does have, to the third power, it is a cubic function after all. So, there's no easy way of solving these sometimes. But this one, you notice, has an x in it again, sort of like the last one does. They all have an x in them. So, what we can do again is factor out an x, leaving 3x squared plus 4x plus 1. That's what that one is. Okay, next bit we're going to do is factor out the square one. So this is, the b is a 4, which we're trying to add to. We're trying to multiply to a times c, which is going to be a 3. Well, we can add 4 and multiply to 3. That would probably be a 1 and a 3. 1 times 3 equals 3. 1 plus 3 equals 4. So that works. Next thing we need to do is to create the little box. That was a little too little. I guess I'll just make it a giant box. Okay. 3x squared with a 1 in here. 1x. 3x. 3x can get factored out here. A 1 here. This one you can factor out an x. This one you can factor out a 1. So this whole thing is x times x plus 1 times 3x plus 1. Okay, so now we figured out what this bottom part is. Now, well, actually the top part, but now we're going to figure out the bottom part. So let me rewrite. Well, we already know what the bottom part is. You can figure it out if you want to, but it's the exact same one I've been using across all the problems. This is just for simplicity, and you're going to encounter many different ones, and I'm just doing these really simple ones right now. So that's what the top one factored to. The bottom one we know is going to factor out to be 2x plus 1, okay, times x plus 1. Okay, now thing is to look for any like terms to cancel out. So let's see if there's an x. There's no x on the bottom. An x plus 1. Well, there is an x plus 1 on the bottom, so those do cancel out. Any 3x plus 1? No. So these, as we can remember, the top ones are going to be our roots, and the bottom ones are going to be our asymptotes. So the roots. So these roots on this one, this is basically x plus 0, so that means 0 is going to be one of these roots. And because if we were to solve this, this would be 3x plus 1 minus 1 minus 1, so that's going to be negative 1. Then we're going to divide both sides by 3, so x equals negative 1 over 3. So negative 1 over 3, and then the asymptotes of this function are going to be negative 1/2. And that's how you figure out these things. Asymptotes will always be on the bottom of a rational function. On the top, those will always be the roots of the function. And this just sort of simplifies it. When I learned this helped me solve the problems and stuff a lot more easily, especially with this factoring method. And I think that's about it for today.